Hi, everyone. Today I want to share with you one of my favorite examples of an early warning system. And this is landslide early warning in Indonesia. And it takes a hybrid socio-technical approach. And that's what I want to explain to you today, the hybrid socio-technical approach and how it has come together in this particular example. Most of this work comes from two publications that you can see here, and the leader of this work was a woman by the name of Karnawati Dwikorita, and I'll talk a little bit more about her later. So we'll start with the example of Indonesian landslides and how this is a template for early warning for all hazards. Then sort of that is consisting of the community involvement, which involves education, evacuation plans, and evacuation drills, some early warning systems, has a broader structure and requires the technical approach, which are the monitoring instruments. And then I'll finish up with just a summary comparison of early warning for all kinds of different hazards that we've already studied this semester. So the key thing about landslides in Indonesia are that they're common, that most of Indonesia is made up of pyroclastic rocks. And if you remember, pyroclastic rocks are the products of pyroclastic flows or explosive volcanic eruptions. And so typically what you have are just layers and layers of these pyroclastic rocks. And so the older ones are impermeable, and that means that the water cannot penetrate or pass through them, and they're sort of hard and packed. The loose stuff, the younger stuff, is this pyroclastic material that can take in water from rainwater, and the water gets in the pore spaces. The water starts to alter that and makes that material heavy. And if you remember from the mass movements chapter, water is a key player in causing slope failure. So at the interface between that packed stuff and the loose stuff, you tend to start getting notches or cracks forming as the slope becomes less and less stable. That is the precursor. So that's the requirement, that you have to have some kind of physical precursor that can be measured in order to predict or give early warning for these kinds of events. And so what they do is they measure the distance across the notch, right? So that's the precursor that can be measured. And then as that notch grows or that crack grows and the growth accelerates, then you can start to get this idea that stability is out the window and that a landslide is much more likely. And then so this whole sort of concept of having a precursor and being able to measure it makes early warning possible. And early warning combined with evacuation, right? So that's the key. Here I just want to show you a picture of what a landslide might look like in Indonesia. You can see for scale, there's a house there in the center of the image. This looks like a lot of mud or dirt that's been remobilized, but remember, it was originally made up of these pyroclastic rocks from explosive volcanic eruptions, and you can see the slip surface there. And so this is a very common occurrence in Indonesia, and they can be rather destructive. So what is this hybrid socio-technical approach? Let's start with the socio part. So the socio part starts with community involvement. And so on the bottom left, you can see a group of people of all different ages in a village working with or listening to a scientist who's the one pointing at the map. And he's telling them kind of about landslides in general. He's going over the map and showing them where landslides might be more likely around them. And you can see just immediately behind them that there's a steep slope, and it looks a little bit like the slope we just saw in the previous picture. And that's probably one of the sources of these landslides that are possible in that village. And then on the bottom right, you see school kids all dressed in green, crowded around the map, and they're also learning about sort of the hazard around them and the possibilities for landslides. The top left is a group of people who are working together, including with scientists, to sketch out the map of the village. And the map on the village is on the right. And so they've put together all kinds of important information about the village. You've got houses where people live in red squares. You have the mosque is the green square in the middle of the image. At the top of the image, you see those arrows and the dashed line. That is where the landslides could be likely or are likely to happen. And then the arrows are indicating ways in which people should travel on the roads to get out of the village. So that's the evacuation part. So this is what is known as a participatory risk and evacuation map. So scientists go to the village. They work with people to educate them about landslides in general, where they are likely, and they all together sketch out this map that you can see on the left. And then the official version is what you see on the right. And so you have color coding by places where you have high risk, which is in pink, lower risk is in yellow. You can see physical characteristics like fractures, and the arrows indicate where mass movements might happen or landslides. You also see the arrows about, and this indicates where people should travel from their homes, which direction they should go on which roads. And what's cool about this is in the bottom, the neighborhoods are divided into the neighborhoods that the village already divides them in, but there are names. So every house has a name associated with them. So they know where everybody lives and everybody's sort of involved with this process. Now, the other thing that you can see here is that there are also monitoring devices. And so we'll talk about those later in a couple of slides, but we have an extensometer, tilt meters, rain gauge, and sirens. And the sirens are the things that tell people to kind of execute the evacuation plan. So then this is an image of them doing evacuation drills. So the volunteers are in orange, and then everyone else who lives there are not in orange, and they're all practicing this evacuation. And so everyone's kind of happy because it isn't a real emergency. But the point is that if you do the evacuation exercise or drills, then everyone's ready when the real thing happens. And this is a really important part of any of these plans to be effective. Okay, so then here we can see the technical part of this, okay? And so on the right, I just have a box and it's a list of instruments, so rain gauge. And so that's the one thing is that you should know that the rain gauge is important because water is this thing that drives mass movements. It turns material to clay. It makes the rock or soil heavy. It weakens the rock or soil. It create slip surfaces, right? So we want to know about rain. The siren is the thing that is used to evacuate people when the time comes. And then the other instruments are extensometers and inclinometers, and these are the things that measure that crack or that little wedge that forms right before or sometime before the landslide happens. So what's an extensometer? So this is a nice sketch. So you have that crack that's sketched through the middle of the image. Then you have a Invar wire is typically what they use, and that stretches across the crack. An Invar wire is simply a wire that doesn't change its physical characteristics with high temperatures or low temperatures, so that if you see an extension of that wire, then that means that the crack is getting bigger. And so the crack would get bigger if the landslide is starting to move a little bit more and more and more. And as that crack gets bigger and as the growth of the crack accelerates, then that's the sort of the precursor that starts to give people the idea that maybe they need to send the warning and sound the sirens. And so what this project did, they also, instead of investing a huge amount of money to buy extensometers from an external company, they started to make extensometers in-house. And they used local skills and parts of products that they already were familiar with, like a dressmaker's tape measure, for example, to measure the extension of the extensometer. So these are images of the box that you would see here on the top right of this image, and that's recording the length or the stretching of that INVAR wire. And so this is one of the approaches, which is to sort of increase the number of instruments by making them locally. Similarly, they did this with inclinometers. And so inclinometers work in the way that's sketched out here. You see that red dashed line is where the landslide slip surface will be, and then the inclinometer gets embedded along that, or vertically in that slope. And then as that inclinometer starts to bend, that indicates that there's some movement on the slide that is the precursor to like the catastrophic failure that leads to the sort of the big slope failure. And so what they did is they ordered a bunch of sensors, and then they made the inclinometer out of things that you can buy at an ordinary hardware store, like PVC pipe and tubing. And so that was kind of an interesting approach. So then they put these things together. So you have the technical aspects on the right-hand side of this figure, and a lot of those instruments were locally made. In addition to that, what they did is that those instruments were monitored by local residents. So those local residents were taking the measurements daily or hourly, and then they were using their cell phones to text their readings to a common website. And that website then was being sort of monitored by scientists, and they were synthesizing the data. And then as that data started to indicate that there could be catastrophic failure because of the precursors, then they would alert the head of the village and they would execute the evacuation plan that the residents already had participated in making. So, in summary, you have sort of the technical system, which is you need to have a hazard map. So you need to know where the landslides might occur, and you need to have an evacuation plan. You need to have early warning equipment, right? You need to make measurements such as rain, levels of rain, because that's often a trigger for landslides, and then measurements of this crack or wedge that develops as these landslides are getting ready to kind of to take off. And then there's the social system, where you have education and participation in making of the evacuation map, practicing in the drills for evacuation, and then broader education through children. So you have this hybrid socio-technical approach, which involves the community from the very beginning and throughout every step of the way. They're involved with the evacuation planning. They participate in drills, they become educated on the physics of landslides, and they are making and reading the instruments that are required to monitor the precursory activity. And so that's a template that I think that can be used throughout the natural hazard systems. So just as a summary here on the Indonesia example, they've then implemented this in this many villages. I don't know, that's tens of villages across Sumatra, Java, and other parts of Indonesia. And so this has been wildly successful for landslides specifically. And this is the woman that made it happen. And I just wanted to kind of give a shout out to female scientists. She is currently the director of Indonesian Agency for Meteorology, Climatology, and Geophysics. So she's pretty high up in the Indonesian government. She was a professor at the University of Gadjah Mada, and she's the first female president of the University of Gadjah Mada. And now she is working on a topic that I had mentioned earlier in this course, which is early warning for tsunami. And so the project that she's working on now is to try to implement some of these elements into early warning for tsunami on the island of Java. And as you know, in 2004, it was devastating to Sumatra to not have any early warning for a tsunami. And south of Java, there is this possibility of an 8.7 magnitude subduction zone earthquake, which is less than 150 miles off the south coast of Java, which gives them 20 to 30 minutes of warning time if they can successfully warn the community and execute an evacuation plan. So that's the big challenge that Dr. Karnawati is working on at the moment. Now I want to make some comparisons. Now that we've looked at this landslide example, I'd like to make some comparisons across a lot of different hazards that we've already looked at in this course. So the hazards are in the first column, and then the early warning time scale. So how much time could you possibly have to warn people of an event that's about to happen? The physical precursor, that's kind of the key to being able to make that warning, the instruments that are used, and then what can be saved or prevented. So for earthquakes, as you remember, we have seconds to minutes, right? So the Japanese were able to save gas lines, bullet trains, data centers. Surgery is one of these big targets. So if someone's undergoing surgery, if they know that there's going to be earthquake waves arriving, they can pull the scalpels away from the patient. And so the key physical precursor is really crazy, but it's the difference in time between the arrival of the P wave and the more damaging S waves and surface waves. And so the instrument are seismometers. And so that's a really, really small time scale, but it's being used effectively for specific critical infrastructure in Japan. Now, tsunami, we know we've looked at, and you've got minutes if you're local, or hours if you're across the other side of the ocean. And the physical precursors are the earthquake or the seismic trigger that generated the tsunami, and then these deep ocean pressure changes. And if you remember, there's the tsunami warning centers, and those consist of seismometers, so they're looking for these triggers. The tsunameters, which are the pressure gauges for deep water that kind of sense the passing of a tsunami in deep water, and then tide gauges, which are used in coastal areas to pick up big waves arriving. And so the things that can be saved are lives, some property, and things like boats that can be sent out to sea before the waves arrive. Because if they're in the harbor, they can be damaged, but if they're in deep water, they're safer. Volcanic eruptions. Volcanoes are sort of really widely varying in their behavior. And so there can be all kinds of different timescales associated with the precursors for volcanic eruptions, hours to weeks to months. And I talked about the different kinds of precursory activity in my lecture, which is ground deformation, seismic activity, and changes in gas characteristics. And so all of those things indicate that there's magma on the move in the subsurface. And the instruments that measure those things, seismometers, tilt meters, GPS, and gas measurements. And things that can be saved are vehicles and lives. And so the key would be to evacuate people before the event becomes deadly. Landslides that we discussed is, the key precursory is some kind of precursory movement and the development of cracks and fractures at the surface. And then a key thing for instrumentation, besides the extensometers and the inclinometers, are rain gauges. And the rain gauges, are important because rain or heavy rains are often a trigger for landslides. And what can be saved are lives and then some types of property like cars and motorcycles. And then hurricanes are a very different system. You've got days or more of potential warning, and the precursory activity is large-scale observable wind patterns that develop, and sort of a very well-developed set of instruments that generally are onboard satellites, as well as weather instruments and modeling. And so lives and some property can be protected by this. And so I wanted to sort of leave you with this table of a summary that kind of puts together a lot of what we've already learned in this course and couches it in terms of early warning and what we can currently do with existing knowledge of the events and existing technology. So thanks for listening.